Well, I'd like to thank Ozzy and everyone else for having me here today. It's nice to be able to speak on this topic to people who can really apply it in your own research. And I'm a psychometrician. I also work with prevention researchers at ASU who deal with Hispanic populations. And you have to excuse me, I'm getting hoarse today from talking. We've dealt with translating instruments into Spanish, and we've also dealt with some of the cultural issues that the previous speaker spoke so well about. I thought that was a great talk. It's going to be hard to follow up that one. And she talked about a lot of what goes into the thinking of designing a questionnaire. And I'm going to talk about kind of the other end of the matter. Suppose you've already done that, you've administered your questionnaire, you've got data. Now you want to know, because maybe you're not so sure still, you want to know whether the data can be interpreted the way you think it should be. And is there any way you can use that data to answer the question? It's more of a validity question regarding comparing groups. And, excuse me. So I kind of set the stage here. Suppose you've got some sort of multiple item scale. It might be a questionnaire or any sort of assessment. And I say multiple item because in this work, if you've only got one item, one question, there's really not much you can do post hoc. You need multiple item measures of some sort to be able to utilize a lot of the tools I'm going to be talking about. And that's usually the case for most of us anyway. We're working with multiple item scales. And you have respondents who can be classified in at least two groups. Usually it's a demographic classification, and that's what you were interested in. We were talking about Spanish speakers, English speakers, but it might be cultural groups or racial groups or nationalities. I've worked with industrial organizational psychologists who survey corporations in 60 countries and have huge data sets involving what essentially are national units and looking at invariance there. So it could be a lot of different potential applications. There's also the question of how surveys change over time and invariance over time, and I'm not going to talk about that. I'm going to focus pretty much on the multiple group issue here, which has been the focus today. And what you're interested in is, can my scale or my items individually be interpreted the same way across these groups? Can the results of these questions, can I take them at face value at the same meaning across these groups? And we're going to kind of nail that question down to its specifics here as we go along. One of the ways of thinking about this is in terms of a latent variable. So you design your questionnaire or your scale or even your item to measure something that you can only measure indirectly. You're asking a respondent to report on their feelings of stress or their depression or their experience in the workplace. And so you're filtering it through their perceptions. But what you're really getting at is a latent variable. We call it latent because we can't directly measure it. And the question you're asking about interpretation is, if I take a Spanish speaker and an English speaker, for example, who are the same on this target latent variable that I intend to measure, would it be the case that those two people have the same expected score on my item or my scale, my test, apart from random error, and we'll nail that down a little bit? Or would it not be the same necessarily, for whatever reason? That's the question of measurement invariance. Given two groups who are in some way matched on the latent variable, two groups of people or two individuals from different groups, would we expect to see the same performance, the same response distribution on a given item or a given scale? And this idea of measurement invariance is, it's kind of old, but it's probably become more important now as more people are surveying different cultures, and we have actually newer questions that come up dealing with, did I lose the mic here? Can you hear me? Not sure what that. It's not my heart. Might be some interference from. Huh? I think so.
Would you like to use this one? This one just goes over the head, though.
Okay, we'll try it.
It's the same, it just goes over the head.
That's interesting. Okay, we'll try this one. Like this? Oh, okay. Try it again. You can hear me out there, right? Okay. So, I'll make sure I'm not too loud here. I'm going to address 4 questions and then give you an example of this kind of research. And the first one is, what is measurement invariance? How do we define it? What does it mean if it holds? What does it mean if it doesn't hold? Second, how do we define it in the context of factor analysis? And I've picked factor analysis to talk about today because that's the most familiar tool of the array of tools people use in this research. That's the one that's probably the most familiar to most of you. Then thirdly, what should I think about as a practical matter before I investigate invariance using factor analysis? And here we're going to talk about some of the practical issues you would think about before you do one of these. And then how do I actually do it? And there I'm going to tie that into an example, and we'll show some step-by-step stuff on how this is done. Can you hear me now? I feel like that phone guy. Okay. So what is measurement invariance? And I'm going to kind of give you a little formal definition. And from time to time, we'll have some equations up here. Feel free to stop me with questions as we're going on. I'm not going to hold all questions till the end. So if you don't understand something I'm talking about, raise your hand, or you have a question related to something I'm talking about, raise your hand, and we can deal with it as we go along. So there are 3 key pieces here to this definition. One is some sort of observable test score, questionnaire, item score.
We changed the battery.
Okay. So we're gonna switch again.
Thank you.
Sure, thank you. Okay. I think we're on, yeah. It might be a test score, it might be a questionnaire, a questionnaire score, it might be a scale score, or it might be an individual item or response to an individual question on a questionnaire. But it's some sort of number or response category. And it's something that we observe, we see, we've got it. W is the latent variable that X is designed to measure. So when you made your questionnaire and you went through that process that our previous speaker spoke about, you allocated certain questions to certain objectives with certain latent variables in mind that you wanted to get at. So W represents those intended objectives, those intended constructs that you're trying to measure. And there may be more than one of them. It's in bold here on the overhead, because to reflect that might be a multivariate, might be multiple things. And then V is a group membership indicator, just to indicate what group a person belongs to. Gender, it would be binary. Cultural groups, it might be polygamous, various categories. So V is also observed. And the question of measurement invariance is, given that we know somebody's status on, or let's say we knew someone's status on W, and we look at the probability of them giving any particular response to a question or getting any particular response on a test, given their status on what we intend to measure. Do we need to worry about what group they belong to? or not? If not, if knowing what group they belong to adds nothing to the reduction of uncertainty, adds nothing to the information beyond knowing W, then we have measurement invariance. So that what counts is what we're intending to measure and what language they speak or what group they belong to or what gender they are doesn't mean anything beyond that. On the other hand, if it does matter, so we got to retain V in the equation down here, then there's something more going on. There's some further influence on the observed response besides our intended construct. So if we're trying to measure depression, but we find that for males and females who are the same on that construct, we get a different patterns of response, that would be a violation of measurement invariance. Now, what the explanation for that would be, we'll think about later. We use probability in this definition because all the modern viewpoints on psychometrics and measurement in one way or another involve probability. The idea being that when you're given a question on a test or you're given a question on a questionnaire or in an interview situation, there's a certain probability you'll give a response. And because of measurement error, you may not give the same response if you were asked another time on another equation or another occasion about that same issue. So it's uncertain. There's uncertainty in there on the best of circumstances. It's not a deterministic process. The question is, do the same probabilities apply given the latent variable for men and women or for these different groups? So here's an example involving depression. I just kind of measured it. Suppose X is an item on a depression scale. W represents the target attribute of depression, the person's actual but unknown standing on this depression construct. And V is a gender indicator. So for a male and female who are identical on W, do we expect that they'd have the same probability of scoring any particular score on X? If X is binary, then they have the same probability of saying yes or no, or true or false. If it's a Likert item, it would be the same probability of any score on that Likert scale. If the answer is yes, then we say X shows measurement invariance in relation to W and gender. Now, if the answer is no, and the item is not invariant, then it must be true that for a male and female who are identical on this latent depression variable, we expect to see systematic differences in scores on that item. And there's a well-known example of such an item on many depression scales. There's questions about crying. I often cry. And that one shows gender differences, as do most items on depression scales. But that item shows a bigger gender difference than we would expect given the pattern of responses to other items. Men usually under-respond to that item. And there have been studies that have shown time after time that that item functions differently for men and women to varying degrees depending on the setting. And so that would be an example of an item that there's something influencing response to that item that has nothing to do with level of depression per se, but is a reflection of other influences at work. If that kind of thing's going on, it clouds interpretation because it seems to imply that there's more being measured than the targeted construct. There's something else going on. That's going to affect then any comparisons of those groups. But it might affect research involving just one group or the other as well, because at least one group it's measuring something slightly differently. So I'll talk about an item. If an item lacks invariance, it's biased. Some people are less willing to use that kind of pejorative term, and we say differential item functioning. The concept of differential item functioning was kind of developed more as a statistical description of the phenomena, saying that this item functions differently in different groups. From a psychological viewpoint, I I like to think in terms of, is it measuring the construct in the same way in the different groups or not, given what you designed the questionnaire or the question to measure. So now I should say some things about what if the item is measurement. And an item that's measurement invariant certainly doesn't mean it doesn't show group differences. So you could have pretty big group differences on a particular questionnaire item, but still the item is invariant. As long as it reflects the differences that are actually there, then it's operating the way it's designed to operate. So measurement invariance doesn't mean that there are no group differences on items. It means that the group differences are a reflection of what the item is intending to measure and differences on that thing. What we don't want to have is group differences that aren't a reflection of our intended construct. And so that would be reflected if you could match people on the depression construct. Those would be differences that would remain after that matching has taken place. Of course, doing the matching, as you might realize by now, we're talking about matching on a latent variable that by definition we can't directly measure. So how could you really do this matching? How could you really decide whether a test or questionnaire item is invariant or not? And that's a really good question, because that goes to the heart of the difficulty in this area of trying to investigate invariance. There are really two broad strategies for doing this, and one of which we're going to talk about today. The other one we won't so much. The first one is, well, to investigate this, you use some sort of measurement model, a latent variable model that models the relationship between the questionnaire items or the observed measures and the latent variable or variables, however many there are. And then you check to see whether that model, within the context of that model, whether the parameters are taking the same value in the two groups, implying that for a given status on the latent trait, you'd expect the same outcome on the observed scores. And there are a number of models one could use. So you've got factor analysis, which we'll talk about. You've also got models from item response theory, which I'm not going to talk about, but that's an item level approach that works well. You've got other latent variable models, latent class models, for example. So there are a variety of such models. The factor analysis one is pretty versatile, so we can talk about that. A whole nother approach to this is to not use any models. And this approach has the advantage that you don't have to worry about fitting models. You don't have to pick the right model. You don't have to have a model. What you do instead is you create some measured variable as a proxy or substitute for the latent variable. It's your best measured guess as to what that latent variable is. And it assumes, of course, that you have such a thing. And then you match individuals on that observed score and look for group differences within the matched groups on the item or whatever it is you're investigating. This is the approach that's used by, say, ETS when it does this kind of thing with their items on the SAT, which they regularly do. Usually the proxy in those contexts is the total score on the test. And there's kind of a bootstrapping process that goes on with winnowing out items that are bad and recalculating the total score until you've purified it to the point where, well, there's some known pitfalls in using that approach. One place where it works well is in really long educational tests where you've got 50, 60 item tests. Because by the time you get that many items in a scale, the reliability of the scale is pretty high. But for the kind of research that a lot of you do, where you're using scales that may be 5 items, 10 items, this isn't a very good approach, because at that level, the reliability is not high often, and one bad item can influence the scale score more drastically with a short test. So the first option may be a better option, but it has some pitfalls as well, as we'll see. So I'm going to kind of move on to the second question now. We've talked about what measurement invariance is. How is it defined in the context of factor analysis? And I'm going to talk about confirmatory factor analysis because that's where the work gets done. We don't really use exploratory factor analysis very much in this work because it doesn't allow you to test specific factor structures and put constraints across groups explicitly, which is the kind of thing you need to do here. So usually in this work now we have a set of items or a set of scores, not just one item, but we're working with multiple items simultaneously or multiple scores. And those are represented here in X. And then W represents the common factor scores on R common factors. We've got P measured variables, R common factors, fewer than P factors here. Maybe there's only one common factor, and that would be the case if your scale, most scales you design to measure one thing, and that would be fine. So R is 1. But you might have a test that has multiple subscales, each of which measures one thing, and maybe you'll analyze them together. Then V is the indicator variable that defines groups. And we're going to use a method of confirmatory factor analysis that allows you to analyze multiple groups simultaneously. Most of them do nowadays. So that isn't a requirement that's very dire. So here's one of those slides where I have a little more technical detail here, but I promise there won't be too many of them here. This kind of expresses the factor model in terms that we can grasp here with multiple groups. You'll notice a K subscript on everything here. That represents the group. So you might have K equals 1 and 2 for males and females, or if you had Spanish speakers or English speakers. Or K could range, however many groups you have. Everything's referenced with the subscript to denote the fact that these things can vary across groups. And X is a string of item scores or subtest scores. There are P of them. And it's expressed in the factor model as equal to an intercept parameter, which is another vector of P constants, kind of like regression intercepts. I'm going to use that analogy a lot. We'll call them latent measurement intercepts, but they're parameters. They're not individual level scores. And then a matrix of factor loadings, lambda. It's a P by R matrix. And then the vector of common factor scores, W, plus some unique factors, or residuals, errors. But in the factor analysis literature, we typically call these unique factors rather than errors. These would include measurement errors, but it would include idiosyncratic influences on individual item scores that aren't necessarily of interest to us. And those could be a source of violation of invariance, as we'll see. So these are actually scores, these epsilons here. And most of the software available for doing this assumes a multivariate normal system here. So you have the common factor scores are multivariate normal with a certain mean vector kappa and a certain covariance matrix phi. And so are the unique factor scores, mean of 0 across groups, and a covariance matrix that may depend on the group. So under the factor model, we had this thing before where we said the probability of responding to any given question depends on W. So here we're kind of saying that When we say there's a normality assumption, we're assuming normal distributions for those latent scores. And there's some formula you can write down for this, which I didn't write down, but some formula F that expresses this probability as a function of these three parameters, which we're going to be very interested in: the measurement intercepts, the loadings, and the unique factor variances. It'll turn out that these are the main three parameter sets that we'll be investigating for group differences in this process. But to the extent that these three parameters depend on K, depend on the group, it means that this probability given W varies as a function of group or as a function of V. We don't have invariance. If we want invariance to hold, it must be the case that this function doesn't depend on K. These parameters are the same across groups: the intercepts, the loadings, the unique variances. If that is true, if all of these are invariant, we say we have strict factorial invariance. That would be kind of the ideal thing. That would be measurement invariance in the factor model, strict factorial invariance. And you'll see that phrase in the literature on this. It's kind of the end point where you'd like to end up if you could. You're hoping that your measure meets that condition of strict factorial invariance. That's as close as you'll come to measurement invariance in the factor model. And you can have that even though there are group differences in the common factor means and the common factor covariance structure. So those don't have to be invariant. That's saying that the common factors vary across groups. Fine. They can vary across groups. What's of interest is, given someone's status on that common factor, say a male and a female who are the same, do they have the same probabilities of scoring anything on the test? And that could be true even though kappa varies across groups and phi varies across groups. So we don't require invariance in those means and factor covariances or correlations. So if strict factorial invariance holds, what does it mean? What would it mean for your data? Well, three things I can think of that are probably of most importance. You could probably derive some other consequences. First, any systematic group differences in the means on the measured variables are then due to group differences on the common factors. By systematic group differences, I mean if you were to do a t-test on the scale scores on your questionnaire and found that, yes, the means differ between males and females on this thing, that difference would be attributable to some difference on the common factors as opposed to something else. That's one thing. Secondly, any systematic group differences in the covariances or correlations among the measured variables are due to group differences on the factors also. So variables A and B, if they show different correlations for Spanish speakers and English speakers, it must be due to the influence of the common factor. It's not an artifact of some violation of invariance. And third, if you regress one variable on the others, or on any subset of the others, and you find those regressions are different, that also must be due to differences on the common factors between the groups. So tests for mean differences, different covariance and correlation structures, and differences in regressions, that covers a lot of the types of analyses that you would probably do on your data. So this is a very good thing. If we could get this to hold, this would be help us greatly in the interpretation of any group differences, certainly. It is, though, a very high bar to get over, as in my experience in years of doing these analyses. What if strict factorial invariance doesn't hold? Then we want to know, well, if strict factorial invariance doesn't hold, what is invariant, what isn't invariant? And we've got some different ways of talking about this, and this is essentially defining vocabulary, the way people talk about this. There's this idea of metric or pattern invariance, which says that the loadings at least the factor loadings are the same across groups, even though nothing else is, even though the intercepts may differ, and even though the unique variances may differ. At a level that's slightly stronger than that, we have this idea of scalar or strong invariance, where both the loadings and the intercepts are the same across groups. If strong invariance holds, then you can compare the means across groups. Any systematic differences in means you can attribute to differences in the common factors. So strong invariance, at least if you can get that far, you've got some confidence in interpreting any mean differences between the groups. What's lacking there is the invariance and the unique factor variances. But what if you don't even get this far? Is there some bare minimum level of invariance that you could look at first? I'll get to that in a minute. Here's a graphic. I kind of like to think of the factor model as a regression model. And this graphic kind of reveals it. If you think about this axis down here is the common factor. Let's say you just have one common factor. This axis is the measured variable. We'll think of it as continuous for this example. The factor model specifies the regression of the observed variable on the common factor. If you have metric invariance, basically what you're saying is the slope of these lines is the same across groups. And here I've subscripted M and F for male and female because I'm using a gender example later. So this would be a case where we have the same slopes for the lines. Changes in the latent variable produce the same degree of change in the observed variable. But the intercepts are different. So there's always a gap between the groups. At any given level of the latent variable, we still have a difference in the observed score reflected by this intercept difference. But it is true that, you know, with the loadings, with the factor loadings being invariant, metric invariance, we do have this parallelism, which is kind of a nice thing. It says that the factor operates kind of in the same way in relation to the observed variable. Now, if you had strong invariance, so you had the same intercepts and slopes, then these two lines would be collinear. They'd lie right on top of each other. The third thing, the unique factor variance, has to do with the variability of scores around each of these lines. And I didn't draw a scatter plot in here to show, you know, what that variability would look like. But to the degree that that variability is the same for the two groups, then the unique variances are the same. And you have invariance in those. So I always tell my students, most of my students come into learning about this, they've already had some regression. So the regression analogy is useful for them to think about, put this in more familiar terms. So if you can't even make metric or strong invariance, there's this notion of configural invariance, which is the starting point for any of these analyses. Here you simply say, well, I think there's the same number of factors in each group, so W has the same dimension in each group, and I think the variables that load on each factor are the same in each group, even though the loading values may differ. So that second point kind of assumes you have more than one factor. If you only have one factor, they're all going to load on that one factor, so the second thing's kind of fulfilled automatically. So what I mean by configural invariance here's an example, very simple, 4-variable, 2-factor example. Here's the loading pattern. You've got variables 1 and 2 load on factor 1, variables 3 and 4 load on factor 2, and these zeros reflect zero loading. So The variables here are restricted to load on one and only one factor, but it's the same factor for the two groups. So at least you have a condition where you have the same number of latent variables and you have the same markers for those latent variables in the two groups, even though they might have slightly different values. You can test this idea in data. You can see whether this holds. If this doesn't hold, then you probably don't proceed any further. You've got a problem. But this becomes kind of a baseline or starting point for the whole analysis to check whether this fits or not. So when we're actually going to do this in confirmatory factor analysis, we start with a configural model and we evaluate the fit of the model to the data, and we gradually, assuming that first model fits, we gradually add in more and more invariance constraints until we can, in a systematic order usually, which we'll demonstrate, until we get to the point where either everything's falling apart or we've reached strict invariance. And along the way, we may identify certain items that are not functioning in an invariant way and others that are. And we may reach a state where we kind of have a partial invariance for some items and not for others. There's some problems trying to identify which items are and which items aren't invariant, particularly the more items you have. But I'm going to illustrate doing all this with an example. That's the easiest way to do it. Excuse me. I picked an example that's small enough that I can get the results on one PowerPoint slide, or at different stages we can see it rather than many variables. So before I get to the example, though, I want to talk about what kind of practical things should I think about before I do this. And some of these might affect the design of your survey study as well. In many cases, in my experience, when I'm called in to do this kind of thing, often it's after the data are collected and I have no say in how the thing was designed. So I'm kind of coming in like a quality control engineer or something, checking to see what the flaws in the building are. It's already built. So I don't have, but if you are in the process of you're a PI or you're designing your study, you can think about these things ahead of time, and that's always better. The most important one is this first one. Do you already have any clear idea of what the factor structure of the scale would be in at least one of the groups? Could be the majority group. If you're doing cross-cultural work in the majority culture or in your own culture, do you really have an idea of what the factor structure is, or do you not have an idea? And many times, people will come to me and say, I've just written a new questionnaire, and I want to do an invariance study of this because I'm going to go out and use it in Spanish speakers, English speakers. Can you show me how to test invariance in this thing? So the first question is, okay, how many factors? What kind of measurement model should we use for this? Well, I don't really know. It's a new questionnaire. Not really certain. Well, at that point I say, well, until you have some sense of it, just within the American culture or whatever culture your starting point is, you really can't initiate this, because if you're going in the dark, what's going to happen is a lot of these models won't fit because you haven't got the right number of latent variables, you don't know what the factor structure is, you can't specify a model that works in order to study whether it's invariant or not. So the first thing you need to do is have some sense of what you're measuring, have some, at least in one group, not necessarily in the group that is new to you and you're studying of interest. So now you may be using a scale that's really well studied in one culture, and that scale we understand. and maybe you don't know how it's going to work in this new culture. That's fine. As long as you have a notion of what the factor structure should be in that one culture, you can test that template in the new culture, and then you'll learn if they're different or if they're not, at least with that point of comparison. But if you have no starting point of comparison, then you're in a weakened position. So it may be premature for you to launch into one of these studies. You may be better off professionally spending some time doing some pilot work, collecting data on this scale in one culture, learning about its structure and its peculiarities, and then carrying it forth. Another question to think about in terms of what you're looking at invariance on, are you going to go down to the item level, or is this invariance at the subtest level, or do you have a battery of whole tests that you're looking at invariance on? What level is the analysis going to take place at? For most of you, it'll probably be an item level analysis. If you've got one questionnaire and your multiple measures or multiple items. If it is an item level analysis, then you need to think about the fact that item scores are discrete. So if you have binary items, they can only assume two values. A binary item scale doesn't fit that factor model, that regression thing that I had up here. It doesn't work so well. You would need a different factor analytic model to study binary items. And a rule of thumb I use is if there's 4 or fewer response categories, you might consider using a different factor model than the one I'm talking about here. The one I'm talking about here is the traditional factor model for roughly continuous measures. It doesn't work so well when the measures are highly discrete at the item level. We do have models that work for that, and we do have software that can use those models in confirmatory and run through the steps that we'll run through, sort of. There's slightly different parameter sets in those. But I'll just warn you ahead of time, if you try to analyze a very highly discrete set of items using one of these continuous models, you can get odd results because of the discreteness of the scale influences. It means that that linear model doesn't really fit, theoretically, to begin with, even if you have the right number of latent variables. So one strategy people try to do to get around this is form parcels of items. So you have a 20-item scale. They're binary items. You know you can't analyze them as binary. Form little parcels of items by summing 3 or 4 of them into little subscales. And then you've gone down to 5 measures, each 4-item parcels, and analyze those as roughly continuous, because with binary you'd have 0 to 10 or 0 to 5, a little better possibility there. The only problem with that is that kind of thing can mask invariance problems, because you're summing these items together and, in a sense, not investigating whether they're individually invariant. And you can have problems with individual items that kind of wash out as you form parcels. So it's not a strategy that is optimal. It would be better, I think, if you're worried about the discreteness, use one of the factor analytic models that is appropriate for those. Another question that always comes up is sample size. What kind of sample size would I need for this? If you have fewer than 100 cases per group, you probably don't have enough to do one of these analyses. Saying that, I've actually done some with fewer than 100 per group, but you tend to run into problems, numerical problems, with these models when you're getting down to that n sample size. So you'd much rather have, a couple hundred per group if you can get it. Now, maybe you can't get it. You might be doing research where it's really hard to get respondents and you just can't make that standard. Then so be it. You can always try doing it with fewer than 100. But the ideal is to have, a couple hundred per group. And if you're doing CFA for the discrete case, 500 per group would be good if you can get it. You don't need to have equal sample sizes per group. Often they'll be discrepant. If you're dealing with cultural groups, you may have problems getting respondents in certain groups. So equal sample sizes are not necessary. Yes?
Okay, so I guess what I'm wondering about with sample sizes, like I'll refer my students to the Preacher website and the Preacher and Kaufman utility on sample size determination for factor analysis, and go through tests of close fit or not close fit, and then we'll get these ridiculously small ends that are needed. And I guess what I'm wondering
is that a power calculation he's doing? Well, if you have enough variables, you can get away with a smaller sample power-wise. So you would also have to enter in the number of variables. I suppose it's possible that power in those CFA depends on the number of variables and the sample size. And the number of variables has a big influence because it influences the degrees of freedom. And as you bring in more variables, you can end up getting bigger degrees of freedom and have a lot of power. But then you've got more tests to do as well. When you get to individual tests of individual parameters, you've got more parameters. And so I'm not sure if I'd use that website for these invariants. I don't know that. I think that isn't that for single group analyses rather than multiple group.
Yeah, I think all you enter degrees of freedom, various RMSEA values,
Yeah,
alpha.
and it's keyed to the RMSEA, right?
Yeah.
Yeah. I'm always dealing with researchers at the lower end of the sample size thing, and I've just developed this rule of thumb that anything below 100, I start seeing problems. And it's more based on personal experience than any sort of calculation I've done. So
I guess what motivates my question is, should there be students here who want to do this for a thesis or a dissertation, and they're required to do some sort of power analysis, and then they have this 50-item measure, and you've got tons and tons of degrees of freedom, and then they put in the numbers, and all of a sudden, I only need 105 people total.
well, yeah, I don't know. There's more to think about than just the power in this, too. I'm thinking about the whole gamut of things. When you get n's down below 100, you have a lot of numerical problems. And the normal approximation that the chi-square fit statistics work with, and the RMSEA as well, starts to break down at those low ends. And I don't know how, you have to factor that into the whole thing too. And you have numerical problems with bad parameter estimates coming up. And so I just try to steer people away from doing really small n.
Would a Monte Carlo simulation be a better way of estimating power?
You could. You'd have to, you could certainly do a simulation M plus to figure out what your power would be, assuming normality and assuming some distributional assumptions. But in real data, it may not be normal, and that may not be a problem when your n is large enough, but when your n starts getting small, then it is a problem. So it can be, I know it's a difficult issue because for a lot of survey researchers, and particularly cross-culturally, it may be hard to get a substantial sample size, and you may just have to work with what you've got. But you can always do a post hoc power calculation. You can always simulate. You can actually bootstrap from your own data and get an estimate of what the power is post hoc. That's another thing you can do without any distributional assumptions. Then another question is what software to use, which now you have a lot more options. 4 of them here: Lizroll, M+, EQS, and Amos. Lizroll and M+ you can use for that discrete case where you have item level data. I'm not sure about EQS and Amos in that case. You can also use MX, which is a little more demanding in terms of programming skill, but it's a free program. And then there's R, which if you know R, you can write your own software or find routines already written that could be adapted for this. So you can do anything with R. But in terms of package programs, Lizroll and M+, and EQS are the ones I've had the most experience with, and I'm going to illustrate Lizroll today with the example we'll look at. So the example I'm going to go through, why did I pick this? This example isn't so relevant to translated instruments and cross-cultural work, but it is an example that, number one, the variables are well-known, well-studied. It's small. It's also, the programs I'm going to deal with here are all on my website, and you can download them, which is nice. And the example's discussed in the book, and it has a substantial sample size. I've got 940 males and 940 females. And this is from the 1980 standardization sample of the WAIS-R, the Wechsler Adult Intelligence Scale. Not the most recent version of this 1980 version. Another reason I picked it is it's not item level. We're analyzing data at the subtest level. So this fits the continuous factor model demands, unlike a lot of item level examples. I'm not even going to use all 11 subtests. I'm only going to use 7 of the 11. And potentially you could use the student version of Lizroll, I think. It'll take 7 variables. You can use the student free version of Lizroll to run these programs, and you can see how they run. Ozzy had suggested, or we'd talked about the possibility of actually running them here, which I could do, but I'm not sure everyone this late in the day wants to sit through running programs, but I have all the programs on slides here, as well as you can download them from this website. The 7 tests are these, and I don't know how familiar you are with the WAIS. There's 11 subtests. Each subtest is multiple item. It's an individually administered test, so it's not a paper and pencil questionnaire kind of thing. You sit there with someone gives you the test verbally with some stimulus materials. And the 7 subtests I'm looking at here are information, which involves questions of general knowledge, like some of them kind of hard to, varying, well-known. These are definitely cultural bound knowledge questions, like what is the Quran, I think is one of them. Vocabulary, which is essentially a vocabulary test. You're to explain the meaning of certain words. Comprehension, which is what should you do in a specific situation, or you're supposed to kind of analyze the situation to explain what you should do. Similarities, where you describe how pairs of nouns are alike. Picture completion, where you're shown a picture and you have to figure out what's missing from the picture. And there's a series of these and they get harder and harder. Picture arrangement, where you arrange kind of these little cartoon panels to tell a story that makes sense. And you're given the panels in the disordered state, and then you have to arrange them. And block design, which is the one I have the most trouble with. You get these colored blocks, and you have to arrange them to reflect a design that you're shown. And then sometimes you have to arrange it to reflect the mirror image of that design, it requires a lot of spatial excellence, which I'm lousy at, especially the mirror image part, where you have to do a kind of a mental rotation of this thing. And so all of these are scored, and then the test as a whole yields two kind of subtest scores, a verbal and a performance, and then a total. And the first four subtests I've listed here are considered verbal. They're considered verbal because the stimulus material is all verbal and the response is all verbal. The last three are considered performance because the stimulus material is essentially pictorial. There's some verbal instruction, but the responses are nonverbal and the stimulus material is not got verbal content. Okay? And these are, in this data set, here are the mean subtest scores. I don't know why I carried them out to 3 decimal places, because it's not really necessary, but these are the mean scores on the subtests for males and females. Males have slightly higher scores. The difference varies by subtest, though. In some differences, in some cases, there's hardly a difference, like similarities, the fourth one down. So you look at these and you ask the question, okay, we have mean differences. Do these mean differences reflect some actual difference in the cognitive abilities we're trying to measure here, or do they reflect some artifact, something other than any real difference? So I said we test a series of models. The WACE has been very well studied factor analytically. So it wasn't designed with any particular factor structure in mind, but there have been thousands of analyses of it going back decades. So for this particular set of 7 variables, pretty confident in saying there's 2 factors. And we'll start out with a 2-factor model, and I'm not going to force each variable to load only on one factor to begin with. I'm going to go with kind of even a weaker model that allows them to load on both factors, but the vocabulary subtest I'm going to force to load on factor 1, and the block design subtest I'm going to force to load on factor 2. So factor 1 I'm thinking is going to emerge as the verbal factor, factor 2 is the performance factor. There's no particular reason for the order there. It could make the other one, could reverse the 2. All the other subtests, they can load where they want. I'm going to let the 2 factors correlate, so there's a little non-zero correlation between these 2 factors. And I'm going to fit this model in both groups, and basically all I'm testing is, are there 2 factors underlying these 7 tests in both groups or not? Does a 2-factor model fit or not? So let's see. Here's I know you can't see this. This is a little small font for you to see. This is the program that tests that model. And this is the one you can download. It's actually a little longer than the later programs, which have more constraints, ironically. So this is actually the longest of the 6 programs I run. But it's not too difficult to come up with appropriate code here. And you can see how I've done it in the sense that I'm analyzing both groups simultaneously. But as far as the data input, I'm inputting one group's raw data and then inputting the other group's raw data as separate files. And in this example, there's no missing data, so I don't have to deal with that. The results of this, in terms of some global fit statistics, so the next one, we're going to make the loadings invariant, taking them just as they are, not forcing each variable to load on only one factor, make the loadings invariant. So this is that metric invariance model. And this is the program that does that. It's a little shorter than the other one. This one doesn't fit as well. All the fit indices got worse. The chi-square is still significant. It jumped up a bit. There's a statistically significant difference, I think, between steps 1 and 2. But this RMSEA value is still in a range that's pretty good, as are these values. They're worse than they were. But in terms of judging model fit, I'd probably retain this model because it's, I should also say, you look at the individual residuals for this, which you can do. Those are printed in the output. And they all look pretty good. There's not an indication that one variable in particular is a problem. So I decided to accept this model and see what the next step would bring. The next step, I wanted to see if I could force the loadings so that I get 2 factors that are pure, just one variable. Each variable loads on only one factor. Sometimes we call this an independent cluster structure. We like to have this because that means that each variable is primarily influenced by only one factor, even though across variables you have more than one factor. And so in doing this, I made factor 1 consist of the 4 verbal tests. Factor 2 are the 3 performance tests. And everything else is the same. The factor loadings are invariant, and they're restricted to be confined to one factor only for each variable. And here's the program that does that. It's, as it turns out, not a very good fit. So here we see what I would consider a substantial jump in the lack of fit. The chi-square goes up into almost 300. This jumps up to 0.09. These don't look so bad, but they're still hovering around 0.05, but they've gotten a lot worse. I always look at the RMSEA as being the main indicator for me as to how the fit looks, and this is definitely not good. The chi-square has definitely jumped up considerably more than it did from the first and second step. So I don't think this works very well for these data. Later we'll see how the loadings do come out. I'll show you what the estimates look like. But what I can conclude here is that this structure doesn't work. This isn't an invariance question, it's more an interpretive question of how those loadings come out. And the one, when looking at the residuals, the similarity subtests seem to be the worst offender with this, but we'll see that later. So next I tried to get strong invariance, make the loadings invariant and the intercepts. And if I can get this, this will be good because then I can compare the means across gender. So going back to the old loading structure, allowing things to load on 2 factors, but now requiring the intercepts also to be invariant. Here's the program that does that. It's a slight alteration of the program, the previous one that had the metric invariance. And the fit here doesn't look that good either, compared to model 2, where we had just metric invariance. The chi-square jumps up. Compared to model 2 was chi-square 31 degrees of freedom, 169. Oop, went the wrong direction. Let's see, model 2 was 26 degrees of freedom, 66. This one's 31 degrees of freedom and 169. So it went from 66 up to 169. Pretty substantial jump. The RMSEA is not as bad as it was in the previous model, but it's still not very good. Anything over 0.05, I start to worry about. These aren't too bad, the standardized root mean square residuals. But I looked at the residuals, and it's pretty clear that one subtest is a problem here, and that's the information subtest. Those intercepts seem to differ across gender. And when I release those, as I do in the next model, now I start to, I've got invariance in loadings, invariance in intercepts, except for the intercept for information, which you can do. You can make some of them invariant and others not. In this case, I release the invariance constraint on information. And this is what I was talking about in reference to partial invariance. It isn't always easy to determine which constraint you ought to release, which particular variable is the offender. In this case, it was kind of easy. There was one that just stood out. But it isn't, you aren't always going to be that lucky, and it can be kind of difficult to determine. So you have to have a strategy for that. I probably don't have time to talk about that, but there is stuff in the literature on how to pursue such a strategy. It's an active area of research, in fact, people looking at different strategies. This model fits much better than the previous one. In fact, this one, if you compare it to Model 2, which was our last model that fit well, this one isn't too much worse than that. It's pretty close. And so allowing that one constraint to be relaxed seemed to make a difference here. So we can kind of say that the problem with that strong invariance was the information subtest. If we make all the other ones but that one invariant, we're okay. And we've just got one final model to do. You might stop here and say, well, okay, I'm done. I know at least one parameter is an invariant for one subtest. But I wanted to see if the unique variances are invariant as well. So I constrained all those to invariance. If we hadn't have had that one problem with the information subtest, this would mean strict invariance, this last step here. And we're almost at strict invariance if this one works. So this one, the fit gets worse, but the RMSEA, the chi-square goes up a little bit. The RMSEA hardly changed at all, nor did the root mean square residuals, the individual ones. So this one's probably acceptable, and we're done, essentially. We only found one parameter that varied across groups, and that was the intercept for the information subtest. I'm going to look at that, the values of that in a minute. Here are the factor loadings as they came out in the last model, and they are invariant, so there's no group difference. You can see that these four are primarily loading on factor 1. These three are primarily loading on factor 2. But with 2,000 cases, these loadings here and here, they're not zero. They're statistically different from zero. So that step where I tried to make them zero didn't work. But they're close to zero, even if I estimate them. I mean, they're pretty small. So these are pretty well identified with their respective factors. I mean, these three are pretty much loading together on one factor, and these four as well. But there's small secondary, and similarities is the one that has the biggest secondary loading here at 0.17. And these are standardized loadings. You have to watch with standardization because you don't want to standardize separately within groups because the groups have different variances. So you use a standardization that is a common standardization across groups, and Lizerl offers that as part of the output. M+ doesn't for some reason, but you can get that in Lizerl. And I'll just mention that the zeros there, those are fixed zeros for identification. So at the beginning of the whole process, remember I said I'm going to force vocabulary to load just on this factor and block design on this one. So I did that by making these zeros. And that's the only constraint on the loadings, and that's true in both groups. Okay, so now coming back to that information subtest, how do you think about the fact that there's different parameters, different intercepts for those? Well, here's a way to think about it, and you won't find this anywhere in the literature except for some stuff I've written, I guess, because nobody really comments on this. But how do you tell whether the effect size for this lack of invariance is big or not for this particular subtest? Here are the gender means for information. This goes back to that earlier table. I just borrowed them off that table. So there's a difference between the gender of about 0.8 on this. The intercept estimates, when you separately estimate them for males and females, are 9.8. It's identical to this. There's a reason for that. And 9.1 for females. So the difference in the intercept estimates is 0.7. And if you look at that difference as a proportion of this difference, in other words, how much of the mean difference is explained by the intercept difference? It's about 83%. So about 83% of the gender difference in means on this test is explained by this artifact that we found for that, measurement intercept difference, which is substantial. I work with, I mentioned I work with some prevention researchers. We spent an entire summer doing these kinds of analyses on translated instruments. And in many cases, we found items that had intercept differences, and they varied in size. And I used this kind of reasoning process to decide when the difference was big enough to worry about and when it wasn't. And I used a rule of thumb of saying, well, if at least half the difference in means is explained by the difference in intercepts, we'll dump the item, get rid of it, if we could. If less than half was, I call that a lack of invariance, but not a big one. That's completely arbitrary. It's my own rule of thumb.
Was that a rule of thumb you published on? Or was that...
It will be published in a chapter that's coming out. It may be in my book, but I know I wrote it in a recent chapter that's in press where I go over how to do this kind of stuff. But it's not a sacred rule. You know, you could adjust that up or down depending on how conservative you want to be.
And those means are at the observed level?
Yeah, those are the observed means, the 9.8, 8.9. And, you know, for me it's kind of disturbing if, talk about a gender difference, but half the difference or more is explained by some sort of artifact that is, we don't have an explanation for it. Now, when it comes to any difference in intercepts, you can kind of engage in this reasoning process. It could be you're using a scale whose metric is so familiar to you that when you see the intercept difference, you can say, oh, that's big or that's small. So if we're talking about, some familiar metric, like, a clinical instrument for depression that's used a lot, where you know where a couple of points on that scale means something. And you find a certain difference in those intercept parameters, those are in the same metric as the observed score. They're just additive constants that shift everyone's score up and down on the observed scale. So you can interpret any difference in those by referencing it directly to the observed scale. Differences in loadings, on the other hand, are a little harder to grasp. If the loadings differ across groups, what does that mean? And what's a big and what's a small difference? That's harder to think about. We didn't find any here, but sometimes you do. I'd say, on balance, having done hundreds of these analyses, the intercept differences are more common than the loading differences. But you do find loading differences, and then you have to think about the size and meaningfulness of those differences. We had an item, one item where we found a mean difference on the measurement difference. We had an item having to do with family conflict, and our samples involved Spanish-speaking and English-speaking Hispanics living in the Phoenix area, all of whom were in the United States, but the Spanish-speaking, the primarily Spanish-speaking ones tended to be more recent immigrants. And we asked an item, we were interested in looking at parenting and family dynamics. We asked an item that was part of a family conflict scale. The item asked how often, it was addressing conflicts between parent and child, how often do you and your child give each other the silent treatment? That is, you're angry at each other and you just don't speak to each other for a while. And we got a much lower frequency of response to that item among the Spanish-speaking. And it was flagged because of an intercept difference here. And in subsequent follow-up with focus groups and so forth, we found that, in the Spanish group, which is more traditional in their parenting styles, the children and the parents see not speaking as a sign of disrespect. That's a highly not a good thing. And they don't do that. That would be very disrespectful if you as a child refused to speak to your parent. And that just doesn't happen. So, they may have a lot of conflict going on, but they're not going to go there. Whereas the English-speaking ones, they did do that. That did happen in their family. And it was more in line with other manifestations of conflict as they arose. But in the Spanish-speaking ones, culturally, that item, it wasn't a translation issue. It was translated properly, but it just referred to a way of behaving that culturally was not right for them. It didn't load on the conflict scale the way it did in the other groups. So, and we didn't think about that ahead of time, but we found out afterwards that that's what was going on. So there's a few final points to consider here. If you do find differences, if you stop somewhere short of strict invariance, you're going to have to look at how big the difference is and calculate some sort of effect size measure. And I showed you what to do with the intercepts. Another question, though, that I didn't talk about, suppose you have a 20-item scale and you have a couple items that aren't invariant. At the item level, there's a difference, but once they're all summed into a scale, what's the impact on the 20-item scale? Well, it may be kind of small. So, it may be that the lack of invariance has very little impact at the level at which you're going to deal with those scores, which is at the scale level. You're not doing analyses at the item level. So sometimes you're dealing with an intact, widely used scale that you didn't create. You find a lack of invariance, and then you face this question. Well, if I get rid of those items, now I'm using a different version of this scale. I can't relate my results to anyone else who's used it. Now I'm off on my own tangent. Or do I keep the items in, but then I've got a problem with this invariance? Well, look at the scale level and see how much impact the lack of invariance has at the scale level. If it's minimal, then maybe you could still use the items even though they're not functioning the same way for the two groups. Very often, though, you're dealing with a 5, 10 item scale, and 1 or 2 items malfunctioning will throw the whole scale off. So then you have a dilemma there. If you're developing a test, that raises the question of what to do if you find items that are lacking in variance. If you're developing a test, you can always drop items, and that's what we did when we were developing some new scales. You can always drop items that show lack of invariance and confine it to the items that don't. The only thing you have to worry about there is sometimes you have items that lack invariance, but the content is so germane to what you want to be doing that, you're kind of loath to drop them. And I had that happen with some of the PIs I was working with on this invariance study. They said, well, that's an item that gets to the heart of what we want to look at. For some reason, it's not functioning the same. You may have to think of something else to do. And then you may not have the luxury of dropping items from existing scales. There's another way to look at the impact of bias on the use of the test. I published an article in Psych Methods 2004 with a guy who was then a grad student. He's now at Texas A&M, Oyman Kwok. We developed a way of looking at the impact of lack of invariance on the use of a test to select people for treatment or select people for jobs or any sort of selection process. If I use a test that has some items or has some content that's biased, what will be the impact if I use that test to select people? And I'll just refer you to that article. It goes into how you can look at the practical impact of the bias on the use of the test. And then I'm often asked, well, can you recommend some articles I can read that aren't too technical on this topic that I could go away and study? There's a lot of technical stuff written, and I know people don't like to read it. But here are two articles that are written in a way that you can read, and they give everything you need to know. The first one by Steve Gregorich appeared in this journal called Medical Care, which is actually a medical journal, but they had a whole issue devoted to bias and differential item functioning research in health disparities research. So that whole issue has a whole bunch of stuff. I wrote an article in there too that looked at kind of summarized the other articles. And his in particular is very good on confirmatory factor analysis, going over what I just talked about in more detail. And then more recently, Jelte Wickerts and Connor Dolan there in the Netherlands wrote kind of a tutorial paper on doing this kind of thing with CFA, and I think it's very good. It's got a lot of pictures, and it's got, clear explanation of what to do and what the impact of invariance or lack of invariance is. So that's another one for you. And then, of course, there's that book that Ozzy showed you, that one I just wrote. That has a lot of stuff in it. It has all what I've said and more, but it also goes into other methods other than CFA. So you can always use that as a reference for all of this. And this example, this WACE example is in there. I did find in preparing these slides, that book just came out, so I discovered my first typo in there. And in the table that gives the CFA results for that example, it should have been 66, it said 88. I think they thought the 6s were 8s or something, but you got the right numbers on these slides here. There's my email and there's my phone if you want to contact me with questions, and thank you for letting me talk.
Are there any questions?
Yes?
Let's say you find partial invariance. How do you interpret that in your results?
Well, depends on where the location of the lack of invariance is, First thing you'd talk about is what the impact of that would be on the kinds of use you'd want to put the test to. So think about what you're going to use the test for. Are you going to do group comparisons? How does the lack of invariance influence those comparisons? And you could have group differences in the unique variances, but have invariant loadings and intercepts. You could still do group comparisons on means, even with those unique variance differences. So it depends on where that lies. And it's also true that I made it a lot simpler than it really is, the process of trying to locate where the violation of invariance is among the variables. For this example, it was relatively simple, but sometimes it's not so simple. So that in itself can be a problem. But partial, you may have a violation of invariance that is statistically significant, but of such small size practically that it really doesn't impede your use of the scale in any significant way. And that can happen, and so then you can argue that, then you look at the effect size and you argue, well, this isn't meaningful even though it's non-zero. It's not large enough to be a problem. I don't know if that answers your question. But.
Yeah, it does. And
Okay.
then you can go ahead and compare means if you think that, well, according to your study, it's not that big of an impact.
Yeah, if the impact is small, you can play out what the impact would be, especially with those intercept differences, because they translate directly into the mean difference. So you have a 30-item test, let's say, and you have one item where there's half a point difference on a Likert scale. Well, the 30 items of 5-point Likert scales, you're going to have a huge score range, and half a point is not going to make a big difference. But it can, sometimes it is meaningful, and then you have to think about what you're going to do about that. There's no procedure. You might think, okay, we identify the bias, the lack of invariance, let's just adjust the scores to reflect that bias. We'll just compensate and scale. Nobody does that, and I don't think that's going to work very well either, because it's not clear how to do that adjustment. So.